All right, this problem is about time and phasor domain relationships. Okay, remember we live in time domain, me, you, and probably most of the people you know. But we have these frequency domain things called phasors, which are really just a tool to abstract some of the math and make it a little bit easier to crunch. So here we're given a time domain signal. V of this generator is 240 cosine 5,000 t in volts. So this is a trig function, so 240 is the peak, right? Well, if they haven't told you otherwise, although they could, in theory, write this trig time domain thing and use a RMS value in here, but here it's peak. So this is a generator V sub G. It's an AC generator, and it's hooked up to a resistor and a cap in parallel. Okay, so this is a 0.556 microfarad cap, and this is a 480 ohm resistor. It's time domain stuff. So we want to find, this is a fun problem. We want to find a bunch of stuff. So we want to find the peak value of the, instantaneous. And they use the word instantaneous. What they're talking about is time domain. So P of t, peak value of the instantaneous time domain, P of t, power delivered, to source. So you could call that P of t max. And then the B, they want P of t min, the minimum value of the instantaneous time domain power delivered to the source. PT max and PT min. Okay, so there's going to be this thing here. PT max is up here, PT min is over here. And this thing might have a phase shift. They want these two thingies here. Then they want the average power, big P, and the reactive power, Q. Then I don't even like this one, but this does load, absorb, or generate magnetizing VARs. Yeah, I don't like that, but anyway, there it is. And then what's the power factor of the load? So they're asking for the phase angle and the reactive factor of the load, which you can also get from the phase angle. Okay, so we need to go to phasor domain here, unless you want to kill yourself with math, trig math. So we'll go to phasors, and we'll generate the phasor V sub G. It's the peak 240 with an angle. Okay, they haven't given you, well, there is no angle here in V of G, so let's just go with that. If they were verbally telling you the peak, then you could assume, here we don't, if you didn't have any angles, you could assume 0, but here there is literally 0 in the math, so we'll go there. But sometimes you can just guess 0 is what I'm saying. So that's what it is rectangularly, just a direct polar. It's a direct translation of the time domain signal. Then let's put that in rectangular. It's going to be 240 plus J 0. So that's phasor domain of the voltage signal. Let's get the phasor domain impedance, because we have these two values, and we have this we have omega. So let's calculate those things. So Yeah, I'm not sure we're out of paper. So Z sub C is we have this formula for the impedance of a capacitor. So it's -1/J. Omega is 5,000. This is omega up here. And the 556 microfarad is minus J360 ohms. Okay, the impedance of the so Z sub C is the impedance of the cap. Okay, what we have here is we have a cap in parallel with a resistor. So we can combine those, and then we would have a voltage phasor and an impedance complex number, and we could solve for I using Ohm's law, and that would give us theta, and we can go into we can get S from that. Just watch. So so we've got a resistor in parallel with a cap. So let's call that Z equivalent. So Z equivalent is it's the well, this guy here, this guy it's just 480 plus J0, right? This thing in phasor format. But that's in parallel with this, and our parallel formula is this product over the sum. So there's 480 plus J0 on the bottom, and then this guy is 0 minus J360. So that's this guy in parallel with this guy in just simplifying using our formula for parallel impedance. And this works out to 172.8 minus J230 ohms. So it's nice to just kind of coalesce all this stuff. So this is VG phasor. There's I phasor going that way through a impedance load of 172.8 minus J230. Just abstract these two elements as a box with this impedance, just to redraw it so we can, not too much, too many things in our head here. Just have a simpler circuit. So we can do Ohm's law now. So we love Ohm's law, right? So Ohm's law, I phasor is Z phasor over V over Z. So it's our voltage phasor is that, and our impedance. So impedance, sometimes I call it a phasor. It's strictly speaking, it's not a phasor. I mean, V and I are phasors. Z is the impedance, but it's a complex number, so I'm loose about that, and I call it a phasor sometimes, but it's not really a phasor. But it is a complex number. Terminology. This ends up being 0.5 plus J 0.667, which in polar form is 0.833, an angle of 53.1 degrees. That's I. So we have I phasor, we have V phasor, and we happen to have this thing. S phasor is given by this. Okay, S phasor is 1/2 V phasor I phasor conjugate, and the conjugate is there to get the angles to work out right. It's kind of lost in the derivation, but you need it. So this is 1/2 240 plus J0. It's a V phasor in rectangular format. And then the complex conjugate of I, here's I, in rectangular form is this thing. The complex conjugate of that is minus J0.667. Okay, just using this formula and flipping the sign of the I to get the complex conjugate of I. It's 60 minus J80. Works out real nice numbers here. Just super fortunate for working the problem any further than that. And if you turn this rectangular into polar, you get 100 angle minus 53.13 degrees. This has units volt amperes. That is not what anything they've asked for, but the thing is, this guy is big P and this guy is big Q, which that they've asked for. So that's part C and part D. Okay. So what did we just do there? We started with time domain. We went to phasor on voltage. We calculated the complex number for impedance. Used Ohm's law to calculate I, and then plugged I and V into this guy, and we got S. And the rectangular form of S gives you the real power, capital P, and the reactive power, Q. What's next? Let's draw it. So before we do anything, so what this thing looks like, P, the big is 60, and Q is minus 80. Minus 80, because it's negative in here. And then this is S. And S is 100. It shows up in the polar form. Also by Pythagoras. It's the hypotenuse of this. And this angle is minus 53 degrees. Okay. We can answer part E. E is, does the load absorb or generate magnetizing bars? And the answer is yes, it absorbs. Well, you could say that it absorbs capacitive bars, or it generates magnetizing bars. I don't like that. It's not super helpful, but write down it's overall capacitive, the load. So that overall capacitive means that we say that it absorbs capacitive bars or generates magnetizing bars. Once again, I don't think it's particularly helpful, but they are asking for that. The the power factor. So F and the power factor is just cosine of theta. So it's cosine of minus 53, it's just 0.6 leading. And the reactive factor is the sine of theta. It's sine of minus 53 is minus 0.8. That's that. Okay, the hard part. So we did part C and D first, and then we did E and F. The hard part is this part A and B, the peak value of the instantaneous time domain power. This time domain signal, the sinusoid here, the peak and the small one. Okay, this one is kind of fun. So, you know what? I'm going to squeeze it on here because part A and B. So we've solved for S. So we've got big P, the real power, and then big Q, the reactive power. So P of T is big P plus big P cosine 2 omega T minus Q sine 2 omega T. So it's 60 plus 60 cosine 2 omega T minus 80 sine 2 omega T. So if you graphed this, so this is just a sine wave. There's a cosine and a sine, but they've broken it up that way so that they can show the 60 and the 80. So they can show that 60 watts is reactive and 80 volt amperes reactive is reactive. But really, remember, if you can add up trig functions and get you can add up sines and cosines and get a single sine or cosine. And there would be a phase shift in there. But that's hidden in here. That's the first thing to realize. The second thing, so if you just plot this, I mean, you could do some more trig on this and prove things to yourself, which I did, but it's not really worth it. So this is P of T as a function of time. So this 60 out front is going to shift this. The second two terms just add up to a single sine wave, and the 60 is going to shift that up by 60. So at 60, that's the average power, or the real power. That's P. That's big P. Then there's a sine wave. No, it doesn't start at 60. There's a sine wave. There's a sine wave, right? Let's put it there. And at 0, this will be 1, and this will be this term will be 1, and this term will be 0, so it'll be 60 plus 60 will be 120 at 0. There's a couple other points that you can figure out, kind of like if I figured out this first one, but it gets really confusing. So the reason I figured that point out is because I don't want you to think that that's the peak. It isn't. The peak. So the complex power has an amplitude of, where's the complex power? S. It has an amplitude of 100 and an angle of 53. That's what. So the 53 is in here. So this would be this thing right here. This distance is minus 53. That shows up. The phase angle shows up. It's negative. You know, for current, it's positive. The current would be ahead of this, but the power is behind it. Or the current is, would be over to the left and the power is to the right. the above and behind, the before and after is confusing, but you know, because remember this is now, and anything to the left is the past, and anything to the right hasn't happened yet. You know, it's the future. So it's confusing on these lagging and leading things. But anyway, that's where that thing is. And then this thing here is 100. That's the amplitude of this, and it's down 100 to this. You should be 100 on top and bottom. I made it too stretchy on the bottom. But anyway, if this is 100, then this must be minus 40, because it's 60 up to the middle of this sine wave, and then it's a sine wave with peak of 100. So once again, I drew it too big here. But anyway, this is 60 minus 100 is minus 40, and this is 60 plus 100, or 160. Okay, so part A. This is part A. This is part A. Answer is 160, and part B answer is minus 40, and it's volt amperes, complex power. All right, so not what you might expect, the shape of the sine wave here, but it has an average value of 60 given by this, has a peak of 100 given by the S thing. And this 60 is the average power. That's what's doing work. But the generator has to send up to a maximum value of 160. And down to a value of minus 40. It's sending a sine wave of an amplitude of 100. But sometimes the power is going forward and sometimes the power is going back. It's weird. All right. That's that problem.